This question is to evaluate integrating rational functions, a logarithmic approach. Evaluate the integral of 1 divided by the quantity x squared minus a squared with respect to x. Give your final answer in terms of natural logarithms and include the constant of integration. First step is to recognize the algebraic form. The expression in the denominator is a difference of squares. That is, x squared minus a squared can be factored into two linear terms, x minus a and x plus a. This is the key to breaking it into simpler parts. Next step is to break the expression into partial fractions. We express the fraction as 1 divided by the product of x minus a and x plus a. This can be rewritten as 1 over 2a multiplied by the quantity 1 over x minus a minus 1 over x plus a. This makes the integral easier to solve term by term. Next step is to integrate each term individually. The integral of 1 over x minus a becomes the natural logarithm of the absolute value of x minus a. Likewise, the integral of 1 over x plus a becomes the natural logarithm of the absolute value of x plus a. So now we have 1 over 2a multiplied by the quantity natural log of absolute value of x minus a minus natural log of absolute value of x plus a. Don't forget to add the constant of integration. Next step is to combine the logarithms. We use the rule that says the difference of two logarithms is the logarithm of the quotient. So we rewrite everything as 1 over 2a times the natural logarithm of the absolute value of the fraction x minus a over x plus a, and finally we add the constant of integration. Final answer is 1 over 2a times the natural logarithm of the absolute value of the quantity x minus a divided by x plus a, plus the constant of integration. Don't forget to factor the denominator before trying to integrate. Be careful to keep the absolute value signs inside the logarithms. Always include the constant of integration at the end. Whenever you're integrating a rational expression with a quadratic in the denominator, try factoring first. Partial fractions often turn into something that integrates directly to logarithms. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel Math Tutor 8285 and turn on the notification bell. Press the like button. Thank you so much. This question is to use of integration by parts. Evaluate the definite integral of the product of the expression t times the quantity 4 plus t and the cosine of 3t with respect to t. First step is to expand the expression. Before starting the integration process, we expand the product. Multiplying t by the quantity 4 plus t gives us 4t plus t squared. So now we're integrating the product of the expression 4t plus t squared and cosine of 3t. Next step is to use of integration by parts. Let's choose u to be the expression 4t plus t squared. Then the derivative of u, which we'll call du, becomes 4 plus 2t. Let's now choose dv to be the differential part, which is cosine of 3t with respect to t. Integrating this, we get v equals 1/3 times sine of 3t. Now applying the integration by parts formula, which says the integral of u dv equals u times v minus the integral of v du, we get the following. 1/3 times the expression 4t plus t squared multiplied by sine of 3t, minus the integral of 1/3 times the expression 4 plus 2t multiplied by sine of 3t. Next step, we deal with the second integral, the integral of the expression 4 plus 2t times sine of 3t. We again use integration by parts. Let's set u as the expression 4 plus 2t. Then do its derivative is 2. Let dv be sine of 3t with respect to t. Integrating this, we get v equals negative 1/3 times cosine of 3t. Now applying the integration by parts formula again, we get negative 1/3 times the expression 4 plus 2t times cosine of 3t, plus the integral of 2 over 3 times cosine of 3t. The remaining integral is straightforward. The integral of cosine of 3t is 1/3 times sine of 3t. So the whole term becomes 2 over 9 times sine of 3t. Putting it all together, this second integration gives us negative 1/3 times the expression 4 plus 2t times cosine of 3t, plus 2 over 9 times sine of 3t. Next step is to assemble the final answer. We now substitute everything back into our original expression. We had the first term, 1/3 times 4t plus t squared times sine of 3t. Now subtracting the second result, which includes two terms. First, negative 1/3 times the expression 4 plus 2t times cosine of 3t. Second, plus 2 over 9 times sine of 3t. Subtracting this full expression is equivalent to adding the first term and subtracting the second one, because of the negative sign in front of the integral. So we get 1/3 times 4t plus t squared times sine of 3t, plus 1 over 9 times the expression 4 plus 2t times cosine of 3t, minus 2 over 27 times sine of 3t. And don't forget to add the constant of integration at the end. That's it for this question. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel. If you're looking for tutoring on final exam level questions, check out my YouTube channel at MathTutor8285. You'll find helpful explanations and strategies to ace your exams. This new question is to find definite integral evaluation by substitution. Evaluate the definite integral of the expression x squared times the quantity 1 plus 2 times x cubed raised to the 5th power over the interval from 0 to 1 using the method of substitution. Make sure to show all steps, including any updates to the limits of integration due to your substitution. First step is to choose a substitution. We're looking at the expression x squared times the quantity 1 plus 2x cubed raised to the 5th power. This setup is ideal for substitution because we see a composite function, that is, something inside a power, and we also notice that its derivative appears nearby. So we let the new variable, called u, be equal to 1 plus 2 times x cubed. Next step is to differentiate to find the differential. We now compute the derivative of u with respect to x. The derivative of 1 plus 2x cubed is 6x squared. Therefore, the differential due is equal to 6 times x squared times dx. But in the original integral, we have just x squared times dx. To match that, we divide both sides by 6. That means x squared times dx is equal to 1/6 of due. Next step is to change the integration limits. Since we're switching from x to u, we need to update the bounds of integration. When x is 0, plug that into the substitution and we get u equals 1. When x is 1, plug that into the substitution and we get u equals 3. So the new limits of integration are from u equals 1 to u equals 3. Next step is to rewrite the integral. Now, the original integral becomes the integral from 1 to 3 of u raised to the 5th power times 1/6 of due. We can factor out the constant 1/6, so it becomes 1/6 times the integral from 1 to 3 of u to the 5th power. Next step is to integrate and simplify. To integrate u to the 5th power, we use the power rule. Add 1 to the exponent, so we get u to the 6th power, and divide by 6. That gives us 1/6 times 1/6, or 1/36, times the quantity u to the 6th power, evaluated from 1 to 3. Now compute the value. 3 to the 6th power is 729, and 1 to the 6th power is 1. The difference is 728. So the result is 136 times 728, which equals 182 divided by 9. A frequent error is forgetting to change the limits of integration after switching variables. Always convert the bounds to the new variable to avoid going back and forth between u and x. When using substitution in definite integrals, always update the limits right after changing variables. It's cleaner, and it avoids common mistakes. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel Math Tutor 8285 and turn on the notification bell. Press the like button. Thank you so much. This new question is to compare two definite integrals. Let I1 be the definite integral from 0 to pi over 2 of sine of x with respect to x. Let I2 be the definite integral from 0 to pi over 2 of cosine of sine of x with respect to x. Which of the following is true? Option A, I1 is greater than I2. Option B, I1 equals I2. Option C, I1 is less than I2. First step is to compare sine of x. We know that for values of x between 0 and pi over 2, the sine of x is always less than x. Also, the sine function is increasing on this interval, so applying sine again to both sides keeps the inequality. That means sine of x is less than sine of x, which in turn is less than x. Now, if we integrate sine of x over the interval from 0 to pi over 2, we get a value that must be less than the integral of sine of x over that same interval. But the integral of sine of x from 0 to pi over 2 is exactly 1. So we conclude that I1 is less than 1. Next step is to compare cosine of sine of x. Now we'll look at cosine of sine of x. Since cosine is a decreasing function on the interval from 0 to pi over 2, and since sine of x is less than x, plugging in a cosine gives us that cosine of sine of x is greater than cosine of x. So if we integrate cosine of sine of x from 0 to pi over 2, we'll get something bigger than the integral of cosine of x over that interval. And the integral of cosine of x from 0 to pi over 2 is also equal to 1. So we conclude that I2 is greater than 1. Next step is to final comparison. We now know that I1 is less than 1 and I2 is greater than 1. Therefore, I1 is strictly less than I2. The correct answer is option C. When you see tricky composite functions inside integrals like sine of x, try comparing them to simpler ones using the idea of increasing or decreasing behavior of functions. It often leads you directly to the answer without doing any difficult calculations. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel Math Tutor 8285 and turn on the notification bell. Press the like button. Thank you so much. This problem is to find integral differentiation by fundamental theorem of calculus. Let capital F of t be defined as the integral from 0 to t of open parenthesis sign of x divided by the square root of 1 plus x squared close parenthesis with respect to x. Find the derivative of capital F of t with respect to t. In other words, compute the time derivative of that integral. First step is to recognize the fundamental theorem of calculus. If capital F of t is defined as the integral from a constant a to the variable t of a function f of x, then the derivative of capital F of t is simply f of t. This is valid as long as the function f is continuous around the point t. Next step is to identify the integrand. In our problem, the integrand function f of x is sine of x divided by the square root of 1 plus x squared. Since this function is continuous for all real x, we can safely apply the fundamental theorem of calculus. Next step is to apply the theorem. According to the theorem, the derivative of the integral from 0 to t of sine of x divided by the square root of 1 plus x squared is simply sine of t divided by the square root of 1 plus t squared. There's a quick tip to remember. When you differentiate an integral with a variable upper limit and a constant lower limit, you could just plug the upper limit directly into the original function inside the integral. That's the beauty of the fundamental theorem of calculus. That's it for this question. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel. If you're looking for tutoring on final exam level questions, check out my YouTube channel at MathTutor8285. You'll find helpful explanations and strategies to ace your exams. This new question is to find region's area and volume of revolution. Let capital R be the region bounded by the curves y equals 5 plus x, y equals x squared, x equals 0, and x equals 1. Part A. Find the area of region R. Part B. Find a volume of the solid formed when region R is revolved about the x-axis. Part C. Find a volume of the solid formed when region R is revolved about the y-axis. Part A. Area of region R. First step is to identify bounds and curves. We are integrating from x equals 0 to x equals 1. The top curve is y equals 5 plus x. The bottom curve is y equals x squared. Next step is to set up area integral. To find the area, we subtract the bottom function from the top. So we take 5 plus x minus x squared and integrate this expression with respect to x from 0 to 1. Next step is to integrate and simplify. Integrating 5 plus x minus x squared gives 5 times x plus 1/2 times x squared minus 1/3 times x cubed. We evaluate this from 0 to 1. Substituting 1 gives 5 plus 1/2 minus 1/3. That adds up to 31 over 6. Final answer for part A, 31 over 6. Always subtract the lower function from the upper one when finding area. Common mistake. Students sometimes reverse the order and get a negative or incorrect result. Part B. Volume when rotated about the x-axis. First step is to use the washer method formula. For volume around the x-axis, we use the formula involving pi times the integral of the outer radius squared minus the inner radius squared, from x equals 0 to x equals 1. The outer radius is 5 plus x, and the inner radius is x squared. Next step is to expand expressions. Squaring 5 plus x gives 25 plus 10x plus x squared. Squaring x squared gives x to the fourth. Now subtract the two expressions. We get 25 plus 10x plus x squared minus x to the fourth. Next step is to integrate. We integrate this expression term by term. The integral of 25 is 25 times x. The integral of 10x is 5x squared. The integral of x squared is 1/3 x cubed. The integral of negative x to the fourth is negative 1/5 x to the fifth. We evaluate all this from 0 to 1. Substituting 1 gives 25 plus 5 plus 1/3 minus 1/5. That totals 452 over 15. Final answer for part B. 452 over 15 times pi. Washer method requires squaring both outer and inner functions. Common mistake. A frequent error is forgetting to square or applying the squares incorrectly. Part C. Volume when rotated about the y-axis. First step is to use the shell method formula. For rotation around the y-axis, we use 2 times pi times the integral of x multiplied by height. Height is the difference between the upper and lower curves. 5 plus x minus x squared. So the full integrand becomes x times quantity 5 plus x minus x squared. Next step is to expand the expression. Distribute the x. We get 5x plus x squared minus x cubed. Now integrate this from x equals 0 to x equals 1. Next step is to integrate that the integral of 5x is 5 over 2x squared. The integral of x squared is 1/3 x cubed. The integral of x cubed is 1/4 x to the fourth. Evaluate the sum of 1. 5 over 2 plus 1/3 minus 1/4. This simplifies to 31 over 12. Finally, multiply by 2 pi, which gives 31 over 6 times pi. Final answer for part C, 31 over 6 times pi. Shell method uses the formula 2 pi times radius times height. Common mistake. Students often forget to multiply by x, which represents the radius. Use top minus bottom for area. Use washer method for x-axis. That means outer radius squared minus inner radius squared. Use shell method for y-axis. That means 2 pi times radius times height. Picture the region first. It tells you what method fits best. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel Math Tutor 8285 and turn on the notification bell. Press the like button. Thank you so much. This problem is to find the volume of a hemisphere by rotation. A circular disk with radius capital R lies in the upper half of the xy plane and is centered at the origin. Consider the upper half of the circle described by the equation x equals the square root of capital R squared minus y squared, where y ranges from 0 to capital R. Find a volume of the solid formed when this semicircular region is rotated around the y-axis. First step is to understand the region. We are working with the right half of the upper semicircle. The curve given is x equals the square root of capital R squared minus y squared. This describes the right side of a circle, where x is positive. The region is bounded between x equals 0 in this curve for values of y going from 0 up to capital R. Next step is to visualize the rotation. When this region is rotated around the y-axis, each horizontal slice at a height, y traces out a circular disk. Since the region starts from x equals 0 and extends to the curve, the radius of the disk at height, y, is the square root of capital R squared minus y squared. That means we are dealing with a solid disk. No hole in the middle. Next step is to area of the cross-section. The area of each circular cross-section is pi times the radius squared. Since the radius is the square root of capital R squared minus y squared, squaring it gives capital R squared minus y squared. So, the area of the slice is pi times capital R squared minus y squared. Next step is to set up the volume integral to find the total volume. We integrate this area from y equals 0 to y equals capital R. That gives us the integral of pi times capital R squared minus y squared, with respect to y, from 0 to capital R. Next step is to compute the integral. We now compute the result of that integral. The integral of capital R squared with respect to y is capital R squared times y. The integral of y squared with respect to y is 1/3 y cubed. So evaluating the expression at capital R gives capital R cubed minus 1/3 of capital R cubed. That simplifies to 2/3 of capital R cubed. Multiply that by pi, and you get pi times 2/3 capital R cubed. Next step is to account for the full region. Remember, this was just the right half of the semicircle. To get the volume from rotating the entire upper semicircle, we double that result. So we multiply pi times 2/3 capital R cubed by 2, giving the final answer, 4/3 times pi times capital R cubed. When rotating symmetric regions like semicircles, always notice whether you're integrating the full shape or just half. Use symmetry to double your result if needed. That's it for this question. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel. If you're looking for tutoring on final exam level questions, check out my YouTube channel at Math Tutor 8285. You'll find helpful explanations and strategies to ace your exams. This problem is typically at the level of a calculus assignment or quiz. If you're preparing for final exam level calculus questions, feel free to check out my YouTube videos linked above. This question is about a particle moves along a path. Described by the equation y equals negative x squared plus 6x minus 5. You're asked to find the area enclosed by this curve and the tangent lines at the 2 points. Point A at x equals 0, where y equals negative 5, and point B at x equals 4, where y equals 3. Please give your answer as an exact value. First, we begin by finding the derivative of the given function, since the derivative gives us the slope of the tangent line at any point. The function is y equals negative x squared plus 6x minus 5. So the derivative, which we'll call y prime, is negative 2x plus 6. Next step, We now calculate the slope of the tangent line at the two specific x values. At x equals 0, the slope is negative 2 times 0 plus 6, which is 6. At x equals 4, the slope is negative 2 times 4 plus 6, which is negative 2. Next step, we use the point-slope formula line to find the equations of the two tangent lines. The first point is at x equals 0 and y equals negative 5 with a slope of 6. So the tangent line at this point is y equals 6x minus 5. The second point is at x equals 4 and y equals 3 with a slope of negative 2. So the tangent line here is y equals negative 2x plus 11. Next, we find the point where these two tangent lines intersect. We set the right-hand sides of both equations equal to each other. 6x minus 5 equals negative 2x plus 11. Solving this, we get 8x equals 16, so x equals 2. Plugging x equals 2 into either equation, we find y equals 7. So the two tangent lines intersect at the point where x is 2 and y is 7. Next step, we now calculate the area enclosed between the parabola and the two tangent lines. We break the region into two parts. From x equals 0 to x equals 2, the upper curve is the tangent line 6x minus 5, and the lower curve is the parabola. From x equals 2 to x equals 4, the upper curve is the tangent line negative 2x plus 11, and the lower curve is again the parabola. So we compute two definite integrals. The first integral is from 0 to 2 of the expression 6x minus 5 minus the original parabola, which simplifies to x squared. The second integral is from 2 to 4 of the expression negative 2x plus 11 minus the original parabola, which simplifies to x squared minus 8x plus 16. Now we compute the area. The first integral of x squared from 0 to 2 gives 8 over 3. The second integral of x squared minus 8x plus 16 from 2 to 4 gives 104 over 3. Adding them together give the final area of 112 over 3. This is the final answer. The exact area enclosed by the parabola and the two tangent lines is 112 divided by 3. Now let's step back and review what we just did. This is a classic type of calculus problem where we calculate the area enclosed between a curve and its tangent lines. Here's what you need to remember. First, take the derivative to get the slopes of the tangents. Use the point-slope form to write the equations of the tangents. Find the intersection point of the two tangent lines. That's your turning point for the area split. Then, set up two integrals. One for the left region, from the leftmost point to the intersection, and one for the right region, from the intersection to the rightmost point. In each case, you integrate the upper curve minus the lower curve. That's the core idea behind calculating area between curves. Finally, always simplify the expressions before integrating, and be careful with your limits of integration. Once you master this workflow, you'll be able to tackle these problems with confidence every time. That's it for this question. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel. If you're looking for tutoring on final exam level questions, check out my YouTube channel at MathTutor8285. You'll find helpful explanations and strategies to ace your exams. This problem is factoring denominators for partial fractions. Determine whether the following statement is true or false. The integral of 1 divided by the quantity x raised to the 4th power plus 1 with respect to x cannot be evaluated using partial fractions. First step is to factor the denominator. We begin by checking if the expression in the denominator, which is x raised to the 4th power plus 1, can be broken down into factors. This helps us see whether we can apply the partial fraction technique. Now, x to the 4th plus 1 may not seem factorable at first, but in fact, it can be factored into two quadratic expressions. One standard way to write it is as open parenthesis x squared plus square root of 2 times x plus 1 close parenthesis times open parenthesis x squared minus square root of 2 times x plus 1 close parenthesis. These two are irreducible quadratic expressions, meaning they cannot be factored further using real numbers. That tells us we can use partial fractions with numerators like a times x plus b over the first quadratic and c times x plus d over the second. So, partial fractions do apply. Next step is to interpret the statement. The original statement claims that the integral of 1 divided by x to the 4th plus 1 cannot be done using partial fractions. But in step 1, we just showed that it can be factored and broken into a sum of partial fractions. The statement is false. Whenever you see a rational expression, try factoring the denominator first. Even if it doesn't look factorable right away, it may split into simpler parts, especially quadratics, that allow you to use partial fractions effectively. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel and turn on the notification bell. Press the like button Thank you so much. This question is to evaluate the integral of x squared times sine of x cubed with respect to x by applying an appropriate substitution method, typically at the level of a calculus assignment or quiz. If you're preparing for final exam level calculus questions, feel free to check out my YouTube videos linked above. First, make a substitution. We let the new variable u be equal to x raised to the third power. Then, the derivative of u with respect to x is 3 times x squared. This means that x squared times dx is equal to 1/3 of do. Next, rewrite the integral using u. Now substitute everything in terms of u. The original integral becomes the integral of sine of u times 1/3 do. This simplifies to 1/3 times the integral of sine of u with respect to u. Then integrate. The integral of sine of u is negative cosine of u. So 1/3 times the integral becomes negative 1/3 times cosine of u. Finally, return to x. We substitute back the expression for u. Since u is x cubed, the answer becomes negative 1/3 times cosine of x cubed, plus the constant of integration. That's the final answer. Let's summarize how to tackle similar problems. When you see an expression where a power of x is inside a function like sine or cosine, and another part of the expression looks like the derivative of that inside function, think of using substitution. Set u equal to the inner expression, in this case, x cubed. Always make sure you can express the rest of the integrand in terms of do. Don't forget to return to x at the end. And finally, describing the behavior of the antiderivative helps you connect calculus with the shape of the graph, a useful visualization skill. That's it for this question. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel. If you're looking for tutoring on final exam level questions, check out my YouTube channel at MathTutor 8285. You'll find helpful explanations and strategies to ace your exams. This problem is to find integral comparison for functions. Decide whether the following mathematical claim is true or false. Support your answer with a clear proof or counterexample. Suppose f and g are continuous functions on the interval from a to b. If f of x is less than or equal to g of x for every x in the interval from a to b, does it necessarily follow that the definite integral of f from a to b is less than or equal to the definite integral of g from a to b? First step is to understand the meaning of the assumption. We are told that f of x is always less than or equal to g of x across the entire interval from a to b. That simply means the graph of f lies below or touches the graph of g throughout this interval. Next step is to use a basic property of definite integrals. The definite integral over an interval gives us the total signed area under a function's graph. A key idea from calculus is, if one function always stays below another function on a closed interval, then the total area under the first one must be less than or equal to the total area under the second one. Next step is to justify this claim with a clear argument. Let's define a new function h, which equals g of x minus f of x. Because f of x is less than or equal to g of x, this means that h of x is greater than or equal to 0 on the entire interval. Now, take the definite integral of h from a to b. That equals the definite integral of g minus the definite integral of f. Since h is always greater than or equal to 0, the integral of h must also be greater than or equal to 0. This tells us that the integral of f is less than or equal to the integral of g. Final conclusion is, yes, the statement is true. Many students mistakenly think this only works if f of x is strictly less than g of x. But this still works even if the two functions are equal at some or even all points in the interval. Whenever one function stays below another over an interval, the total area under its graph, meaning the definite integral, will also be less. Think of it as comparing the height of two hills. The lower hill covers less area under it. That's it for this question solving. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel and turn on the notification bell. Press the like button. Thank you so much.